Hello dear students, this is grade 12 mathematics lesson on unit 4 application of derivative. On today's lesson we focus on application of derivative in determining shape of graph. So after revising this lesson you are expected to determine increasing and decreasing interval of a function using derivative, and after that you are also expected to determine concavity interval and inflection point of a graph. Now let's see these concepts one by one. Okay, increasing and decreasing test. Suppose that f is continuous on an interval I and it is differentiable in the interior of I. Then if the derivative of the function is greater than or equal to 0 for all x in the interior of I, then f is increasing on that interval. Look, if we have this function f of x, the derivative of this function from the right side of this part is positive, because you know derivative means it is the slope of tangent line. If you draw a tangent line for at this point, you will have this one tangent line like this. So the slope of such line is positive slope, or that means the derivative of this function is greater than or equal to 0 for the right part of a. Therefore, this function is increasing. And if f derivative of x is greater than 0 and the derivative is 0 only for finite number of points on I, then f is strictly increasing in this case. Look, the derivative of this function at a, at a finite number at a is 0. So this function is strictly increasing from a to infinity, because the derivative is 0 at finite number a, and for the other part it is greater than 0. Therefore this function is strictly on this interval. But if you take this one, this function, look this, if you take this function, the derivative of this function, as you can see, the derivative is the slope of this tangent line. The slope of tangent line is positive everywhere here, it is positive. But for this part, for this part, the slope or the derivative of this function is constant, is 0. The derivative of this part will be 0. The derivative of our f of x, it is 0 for this interval, from assume this point is a for b. For this interval, since the derivative is 0, this interval is not finite. Therefore, this function is derivative for every point it is greater or equal to 0. But this function is not strictly increasing, because the derivative is 0 at some infinite points. But if the derivative is 0 at finite point, that function will be strictly increasing. Now let's continue the other part. Okay, if f derivative of x is less than or equal to 0 for all x in the interior of I, then f is decreasing. Geometrically, you can see this one. If you take this function for this interval, the slope derivative, the slope of tangent line will be like this. So the slope of such line is negative. Therefore, the graph is decreasing for this part. Here it says if for the derivative of the function is less than 0 for all x, in that case the function is decreasing. Okay, now let's see the next one. If the derivative of the function is less than 0 and is equal to 0 only for finite number of points on that interval, then f is strictly decreasing on I. Now let's see example for this concept. Here say let CB is a critical point of f, then 1, if the derivative of the function changes its sign from minus 2 plus at c, then f of c is a local minimum point. Look this one graphically. Let's take this function. This point is a critical point because the slope of tangent line at this point, the derivative at c is 0. C is a critical point. And the derivative of this function is changing from this part is decreasing, or it is the slope of tangent line for this part it is negative, and the slope of tangent line for this part is increasing, or if you take tangent line for this one it is positive. The derivative of the function, if it changes from negative to positive at the critical point, then this point, we call this point local minimum point, local minimum point. Now let's see the next one. If f derivative of x changes the sign from plus 2 minus at c, then f of c is a local maximum point. We can also see this graphically. Look this one. We have this function. At this point, f derivative of the function at c is 0. So this is a critical number. This is a critical number. So the slope of tangent line to this graph from the left side, if you take from the left side, it is positive. And the slope of tangent line to the right of the critical number will be like this, therefore it is negative. So the derivative of the function is changing from plus to minus at the critical point. Therefore, this point is this local maximum point of the given function. And if f derivative of x does not change sign at c, then f has neither local maximum nor local minimum value at that point. Now let's see example for this. Let f of x is given to be this 3x the power of 4 minus 4x cubed minus 12x squared plus 5. Then find the interval where f is increasing and decreasing. So to do this, we need to find the derivative and the sign of derivative of the function. And we are asked also to determine local maximum and local minimum values. So let's see the solution. We need to find the derivative of this function. The derivative of our function f of x, this is equal to the derivative of this one is 12 times x cubed, 12x cubed minus the derivative of this one is this 12x squared minus the derivative of this one is this 24x, 24x. The derivative of 5 is 0. So the derivative of our function f of x, this is equal to, we can take 12x as a common factor. So 12x into, we have x squared here minus x and minus 2. So this is equal to 12x and factorizing this, you'll have this 1 x minus 2 and times x plus 1. This is the derivative of our function f of x. So to determine increasing and decreasing interval, we need to know or find the sign of this value. So to find that, I have to use sign chart. So let's use sign chart. We will have x equal to -1 at this point, x is equal to -1, and x is equal to 0. We need to find the critical numbers or the value of x that makes this function 0. And in order, we need to put in order -1, 0, and 2. And we'll have this 12x here, and x minus 2, x plus 1. 12x is 0 at this point, and to the right of this, when you put 1, for example, 12 times 1 is positive. To the right of 0, 12x will be this positive. To the left will be this negative. And x minus 2, it is 0 when you put 2. If you put a number greater than 2, it will be plus, and for other part it will be minus. X plus 1 will be 0 at x equals to -1, and it will be plus for a number greater than -1, and it will be negative for x less than -1. So now I need to find the sign of the product. So here it is 12x times x minus 2 times x plus 1. So for this part, the product will be this minus times minus times minus. It will be minus. And for this interval from -1 up to 0, the product will be this plus, and we have 0 here. We have 0 at the boundary, and the product of this gives you plus times plus will be this minus, and here at the boundary it is 0, and then here it is positive. Therefore, from this you can see that if derivative of x is greater than or equal to 0, if derivative of x is this greater or equal to 0 on the interval, closed interval -1 up to 0. It's from -1 up to 0, from -1 up to 0, and from 2 up to infinity, from 2 up to infinity. Therefore, the function is, it is increasing on this interval. It is increasing on from -1 up to 0 and 2 up to infinity. It is increasing on this interval. And our function f of x is negative on this interval. If derivative of x is this less than or equal to 0 for the interval from -infinity up to -1, from -infinity up to -1, and from 0 to 2, from 0 to 2. Therefore, our function is strictly increasing on this interval. It is strictly increasing on this interval because the derivative is greater than or equal to 0. Strictly increasing on this interval. Since the derivative of this function is 0 as finite number, so we can say strictly increasing. And on this interval, the function is strictly decreasing, strictly decreasing. Strictly decreasing. Okay, now the next question we are asked to find is this: the local maximum and the local minimum points and values. From this, you can see that -1, 0, and 2 are the critical numbers because the derivative of this function is 0 at these numbers. Now, at critical number -1, at the critical number -1, the derivative is changing from -2 plus. -2 plus means just the curve is just moving like this. This -2 plus. So at this point f of -1 will be this local minimum point. So from this f of -1 is it is local minimum. Local minimum point. And the other critical number is 0. At 0, the derivative is changing sign from plus to minus. It's changing from plus to minus means just the curve is moving like this. The derivative is changing from plus to minus means it has a local maximum at that point. So f of 0, from this you can see that f of 0 is it is local. It's local max. And this one at 2, the derivative is changing its sign from minus to plus. So minus to plus means it is moving like this. So it has a local minimum point at this. So f of 2 is it is local minimum. So this is the first example. We'll continue to the next one. Okay, now here consider the graph of f derivative of x below and determine the interval where f is increasing and decreasing and the local maximum and local minimum values. Look, the graph given is this one. Assume this is a graph of, it's not the graph of f of x, the graph of f derivative of x is given, and this point is it is a, and this point it is b, this point it is c. So here we are asked the interval in which the function, our function f of x is increasing and decreasing. First, let's see the interval where the function is increasing. So to find the interval in which the function is increasing, we need to find the point where, or the interval where f derivative of x is greater than 0. From this graph, this is a graph of f derivative of x. So from a to b, you can see that f derivative of x is above x-axis. That means it is greater than 0. Not only for that, from c and infinity, the graph is, or f derivative of x is above x-axis, means f derivative of x greater than 0. So f derivative of x is greater than 0 for the interval for the interval from a to b. From a to b. And from C2 and from C up to infinity. So for this interval, the graph is above x-axis or greater than 0. The derivative of this function greater than 0. This means that it's increasing, or it is strictly increasing on this interval. Therefore, our function is strictly increasing on this interval. Now, our function f derivative of x is this less than or equal to 0 means this is a graph of f derivative of x. Less than 0 means the point where this function is below x-axis. Therefore, f derivative of x is less than 0 or below x-axis for the interval negative infinity up to a is below x-axis, and from b to c also below x-axis. Therefore, here f derivative of x is less than 0 for the interval from negative infinity up to a is below x-axis, and from b up to c also below x-axis, and from b to c. Since the derivative of the function f of x is less than 0 on this interval, so our function is strictly decreasing on this interval. And in addition to this, we are asked to find the local maximum and the local minimum values. To find that, we need to see the critical numbers. The critical number is a point where the derivative is 0. Our f derivative of x is 0 from the graph at this point. The derivative of this function is 0 at this point, at b and at c. So these are the critical numbers. So at x is equal to a, at x is equal to b, and at x equals to c, the function or f derivative of x is 0. So these are critical numbers. So 1, at this critical number, the derivative is changing its sign from this one is below x-axis, its derivative is negative. That means it's changing sign from negative to positive. So if change sign from negative to positive is like this, so this point is local minimum point. Therefore, f of a is local minimum. F of s is local minimum. And at b, you can see the derivative is changing. This one is positive and this one is negative. It's changing from plus to minus, like this. It is plus to minus. So this point local max. Therefore, f of b from this is f of b is this local max. F of b is this local max. And f of c is the derivative changing sign from minus to plus. Minus to plus means this local minimum. So f of c is this local minimum point. So this is it. We'll continue to next part. Okay, the next part is concavity and inflection point. Before concavity test, let's define the terms what concavity and inflection point means. Look this one. If we have such type of curve, if we draw any tangent line to this curve, it will be this above this tangent line, and therefore this curve we call this concave up. If you take this one and draw tangent line to it, the curve will be always below the tangent line. So in this case, we call this concave downward. This part will be this concave down. And the point where concavity changes, we call it inflection point. This point is a point where the graph is concave up and changes this concavity at this point to concave down. So this point we call it inflection point. Therefore, the point where concavity changes, we call this inflection point. Now let's see how to determine the interval of concavity or concave up and concave down of a given function. Let f be a function which is twice differentiable on interval I. Then if the second derivative of the function is greater than 0 for all x in that interval, then the graph is concave upward. So to determine the interval for concave upward, simply you see the sign of the second derivative. If the sign of second derivative is greater than 0, so on that interval the function is concave up. And if the second derivative of the function is less than 0 for all x in that interval, then the graph of f is concave downward. It is concave downward. And the point where the concavity changes, we call that inflection point. And let's see second derivative test to here. Suppose f is twice differentiable and c is critical number. Then if the second derivative of the function as c is greater than 0, then f has local minimum at c. If the second derivative greater than 0, then the function will have local minimum at c. And if the second derivative is less than 0 at c, then the function will have local maximum value at c. If the second derivative at c is 0, then the test fails. That means the test, it doesn't tell you whether the function has local max, local minimum, or neither at that point. So the test fails if the second derivative at c is 0. Now let's see example. Here, discuss the behavior of the curve f of x is equal to x to the power of 4 minus 4x cubed with respect to concavity and points of inflection and local maximum and minimum values. Now let's do this question together. So to find the concavity interval, we need to find the second derivative of this function, the sign of second derivative of this function. So the first derivative of our function will be equal to, it is 4x cubed minus the derivative of this one is 12x squared is for the first derivative. From this I can put the critical number. So the first derivative of this function will be equal to, let's take 4x squared as a common. 4x squared as a common. You'll have x here minus, we have 3 here. Okay, from this you can see that x is equal to 0 and x is equal to 3. These two are critical numbers. But to determine the concavity interval, we need to find the second derivative of this function. So the second derivative of our function is equal to this. Take the derivative of this one, it will be this 12x squared minus the derivative of this one, it is 2 times 12 is 24, 24x. So we need to find or check the sign of this second derivative. So let's take 12x as a common. You'll have here x minus 2. So to find the sign of this, we have to use sign chart. So using sign chart, you will have this one. The boundary numbers 0 and 2. 0 and 2. and our function here will have 12x, x minus 2 here. So the sign of 12x for x less than 0 is negative. It will be 0 at x equals 0. For the other part, it will be this positive. And x minus 2 is this 0 for x equals to 2, and positive for this part and negative for this part. Now let's see the sign of the product 12x times x minus 2. The product of this two is positive. Here it is 0. This one is negative. This point is 0. The product of two is positive. So from this, you can see that the second derivative of this function is positive for 2 greater than 0 and less than 0. Therefore, here the second derivative of our function f of x is greater than 0 for the interval open interval 2 up to infinity and negative infinity up to 0. Negative infinity up to 0. Therefore, for this interval, our graph is this concave upward, since second derivative is greater than 0. It is concave upward. And for this interval, the second derivative from 0 to 2, open interval 0 up to 2, the second derivative of our function is this less than 0. It is less than 0. Therefore, for this interval, our function it is concave down, since second derivative is less than 0. Concave down. Okay. Now what remains is we need to find the local maximum and local minimum and maximum values or points. So to find that, we have the critical numbers x is equal to 0 and x is equals to 3. So here using second derivative test, we can check whether this point x equal to 0 and x is a critical number. These are the critical numbers. The derivative where 0, this is a critical number. These are the critical numbers. We can check these critical numbers whether they are local max or local mean using the first derivative test. But let's use now second derivative test. So the second derivative of our function is, it is given by this expression 12x squared minus 24x. So the second derivative of our this function at x is equal to 0 is this 0. Therefore, we don't know whether this is this local max or local minimum point using second derivative test, because it is 0, the test fails. So to check that, we need to use a first derivative test. Please students, check whether this point is a local max or a local minimum point using first derivative test. We have first derivative here. Check the sign, and if the sign changes from plus to minus at this critical point, it will be this local max. If it changes sign from minus to plus, it will be local minimum. So check by yourself. Now let's check x equal to 3 using second derivative test. For 3, the second derivative at 3, this equal to this 12 times 9 minus 24 times 3. This equal to 9 times 2, it is 18. 9 times 1 is 9 plus 1, it is 108 minus 3 times 4, 12, 3 times 2, 6 plus 1 is 7. So this is positive. When you subtract, this gets positive. Since the second derivative at 3 is positive, this function has a local minimum at this point. So f of 3 is this local minimum. Therefore, it is f of 3 is this local, it is local minimum. Now, let's summarize what we have seen today. The basic point that we have seen today is the first one. If the derivative of the function is greater than 0, then that function is increasing. If the derivative of the function is less than 0, then that function is decreasing on that interval. If the derivative of the function changes the sign from minus to plus at c, then f of c is local minimum. It is a local minimum value. If the derivative of the function changes its sign from plus to minus at c or at the critical point, then f of c will be this local maximum. And if the second derivative of the function is greater than 0 for all x in I, then the graph is this concave upward. If the second derivative is positive, the graph is concave upward. If the second derivative of the function is this less than 0 for all x in I, then the graph will be this concave. It is concave downward. So this is all about today's lesson, and I'll give you questions for you. Please try these questions, and in addition to this, please read examples on page 179 up to 183 and do exercise 4.3, 4.4 and 4.5, which are found on page 177 to 188. So it's all about today's lesson. Until next lecture class, goodbye.